Okay, so now next speaker, Dr. Rajeev Gangula from Northeastern University. And that also another institute, I know Mary talked about it in the morning, but they're also very much into experimental open regime, open source, and Tommaso Melodia is leading that. And I'm glad, Rajeev, you could come and talk about what's going on, how people can take advantage of the facilities you have. Please.
Thanks for the introduction and inviting me. Good afternoon, everyone. So I come from the wireless.
If you want to walk around, you can just use this.
So I come from the wireless Internet of Things Institute located in the Northeastern University. It's basically a research and education hub, primarily focused on smart and interconnected systems. We have a special emphasis on wireless testbeds and experimental research. So the institute is funded by many sponsoring agencies, and also there's a strong industrial partnership with the institute. So what we think, some of the key enablers for the 6G technology, first one being the spectrum. As you know, the FR3 is opening up for the 6G, and spectrum sharing on real-time scales is very important. And what's already been discussed in the ORAN, which is the Open Programmable Networks with AI native control, which is already in ORAN, so it's going to stay in 6G. Another thing that I want to highlight is that not just the communication, but 6G is expected to offer sensing and position capabilities too. So I'm going to present this Open6G Center. So basically, it's an industry, university, government initiative. It's an Open6G Center located in the Burlington Northeastern University Innovation Campus. So the idea is to have a research and development center that focuses on programmable and disaggregated 6G networks. So the idea is for researchers, especially, is to use these wireless testbeds and tools to come up with not just for the academic papers involving the theoretical algorithm research, but actually put them into practice with an end-to-end demonstrations and proof of concepts. So we are also an OTIC center, ORAN certified OTIC center. So these are the couple of platforms. I think some of them are mentioned by Marie in the morning. So Colosseum, which is basically a big RF emulation platforms. And then we have an Arena, which is an over-there platform using several SDRs, mainly USRPs. And the another one is the X5G. Actually here, you can see. So here, actually, we are integrating several different components of the ORAN. For example, commercial RUs and, let's say, the DU accelerators, and integrating with the OpenAI interface, and doing an end-to-end 5G connection that is operable with the commercial UEs. So a bit more about Colosseum. Basically, it's a big wireless emulation. It has 256 software-defined radios, and all of them can be connected by a massive channel emulator. It's called MChem. And you can do, the idea is to have, you can do big, large-scale wireless experiments, repeatable in a more controlled manner. So for example, with now we are able to deploy an end-to-end 5G network consisting of the core network, the CU-DU split, and an RUE. All of them are running the OpenAI interface for now. So based on these wireless testbeds and the infrastructure we have, as I said before, the idea is to have not just research on the theoretical part, but come up with these end-to-end demonstrations. So here I'm going to talk about this couple of topics. So spectrum sharing and DApps and the positioning. So first I'm going to introduce the concept of DApps and how this can be leveraged in the spectrum sharing. So as you know, in ORAN, you already know that there are several RApps and XApps doing this intelligent closed-loop control. As you can think of, the RApps operate at higher level, so basically extracting infrastructure level KPIs, and they operate on order of scale, order of seconds. So then we have the XApps, extracting a bit lower level KPIs in the CU and DU. When it comes to DU, it's basically the MAC level, for example, the resource utilization or the buffer stats. So these XApps operate at tens or 100 milliseconds. So these XApps are integrated with the real-time rig over the E2 interface. But the concept of DApps goes even down further the stack. So for example, you want to extract very low-level KPIs, for example, from the hi-fi. So for example, you can estimate the channel estimates or the IQ samples from, let's say, some channel that you want to so here, the nature of the KPIs is very different in the sense that these KPIs are very heavy. So if you want to extract IQ samples, they can be on the order of megabytes or gigabytes. And also the control that you want to do is very time critical. You want to do on the order of less than 10 milliseconds. So as you might ask, why do you want to do these DApps? Especially because, as you have seen from the several talks in the morning, the AI ML is not just on the network orchestration part, but is also entering currently evaluated both in the 3GPP and also in the AI RAN Alliance, introducing these AI ML blocks in the L1 and L2 layers. So for example, if you want to do this CSI estimation, beam management, or if you're designing decoders and encoders based on the AI ML blocks, especially in, for example, if you can think of semantic communications where the AI ML plays even bigger role. You want to do spectrum sensing and integrated sensing conversion. So these are the couple of applications where you want to extract these lower level KPIs, and then you want to run the inference algorithm. So this is currently on the discussion in the ORAN Alliance standardization. Several partners are also contributing to this research effort. So the difference that I want to highlight between the XApps, real-time rig, and the DApp. So unlike the near real-time rig, we think the DApps are mostly collocated with the DU. Why? Because mostly it's nature of the KPIs that you're extracting. So if you're extracting very low-level, IQ-level data, so one of the things is that you're really intensive data, and the timing loops and the control loops are on the order of milliseconds, and also maybe the security aspects. Maybe the operators doesn't want to expose these DU IQ samples to an outside entity. So then I'm going to present a use case of these DApps in the spectrum sharing scenario. So currently the spectrum sharing is done in the CBRS band, but you can imagine in 6G with FR3, it's going to play even more crucial role. So the CBRS band is a 150 megahertz band between 3.55 to 3.7 gigahertz. It completely overlaps with the N77 and 78 band of 5G. So the game here is that there are incumbent or priority users, basically the government systems, and then you have these licensed 5G applications. So the 5G, the licensed users can use the spectrum when there is no actually any primary user presence. So currently this is managed by a central authority. It's called the Spectrum Access System that coordinates in a central manner the spectrum sharing. And this relies on dedicated environmental sensors. So you can think of these dedicated sensors placed along, for example, along a coast, will detect the spectrum or sense the spectrum, and if there is any primary user, this will relay back to the SAS, and SAS will coordinate the spectrum sharing. But as you can think, because this is a dedicated special infrastructure, so here you can think of there are two different entities. One is a cellular network, the other one is a spectrum sensing network. Typically, these things are very slow to react. So especially if you want to focus on 6G and real-time spectrum sharing applications, this kind of system might not be efficient. So on the other hand, we already seen there are several intelligent control loops in ORAN, right? So the natural question is that can we use the ORAN ecosystem for the spectrum sharing? So this is similar to one of the talk earlier by Venki. Can we use the RAN as a spectrum sensor, right? So can we use the G node Bs or RUs not just for the communication, but also for sensing? It's good that thanks to TDD, since the uplink and the downlink operate on the same frequency bands, so we can do what we call like a listen while talking approach. So there are some symbols. For example, if you can think of a slot consist of 14 OFDM symbols, you can use many of them for the communications, but you can reserve some for the dedicated sensing. So in these sensing symbols, there won't be any transmissions, or there is no UE being scheduled. So you get these IQ samples from these sensing symbols, and then you can do some inference algorithm. So basically, you can detect if there is a just interference or noise, or there is an actual incumbent user presence where the G0B is operating. If the user is active, then you can think on which resource block exactly the primary user is active. So this is the concept that we have come with, a prototype. So basically, it's a DApp-based spectrum sensing. We use the OAI G0B here. So here we have the OAI G0B, basically the DU part, and then the DApp, which is collocated along with the DU. And they both interact through an called agent, what we call an E3 agent. So the idea is that the DApp will ask for these IQ samples from this sensing symbol. Once you get these sensing symbols, the DApp can run the inference algorithm and inform this OAI G0B about this on which resource block there is a primary user actively transmitting. So all the communication is through this E3 agent. So here we are using in the demo G0B operating on N78 band, 40 megahertz at 3.6 gigahertz frequency. So what the control action will be is that once you get this list of resource blocks where the primary user active, we have to update the scheduler at the G0B. Either you want to blank these PRBs or you want to do bandwidth part switching, in the sense that if there is a bandwidth part where the primary user is active, then you want to kick out all the users from this bandwidth part and you send them into a different bandwidth part. So this is the demo that we have submitted to Milcom. So just a simple sneak peek. So here we are running OAI G0B, running DApp, running on the same machine together. And this is the priority user doing some transmission at this frequency. So this is immediately detected by this here, by the DApp. And then the DApp can inform the OAI G0B. For example, I don't know if it's visible, but let's say this PRB number 77 is barred or blanked. So this is the first use case that I want to mentioning. And second one, I want to touch upon the positioning with the open interface. So open interface supports reference signals, both in the uplink and downlink, sounding reference signals and the positioning reference signals. Based on this, we can do some sort of localization or positioning techniques, such as time difference of arrivals and the round trip time. And the network side of it, for example, the NRPPA and LMF part is currently being implemented in OAI. But I'm not going to talk about this architecture, but mainly about this one of the new method that we have introduced and tested with OAI, a novel method to obtain the round trip time. So the standardized round trip time method requires the UE to do some timing measurement in the downlink, and then it has to report this back to the network, right? So ideally, this involves latency and overhead. Our idea is that can you reduce this measurement reporting back? So here we have used a trick of sending the SRS signal immediately next to the random access signal. So this avoids the control loops. And then we are able to obtain the RTT measurement without actually UE doing the measurement reporting. So for this, we have introduced like a new DCI command. And once you get the DCI command, you can perform certain actions and send the SRS. So one cool thing about it is that since this is not standardized, you cannot use any commercial UE. This is where the open source really comes into picture. So we have used the OpenAir G0B, OpenAir UE, both here. We have implemented the signaling mechanism, and we have done the experiments. So first, we have validated with the real-world experiments in an anechoic chamber. So we validated that our signaling mechanism works, and we are getting the expected round trip times. But as you can think, the outdoor experiments are very time-consuming, and many of those researchers don't have these facilities, right? So ideally, we want to exploit the test bed that we have, which is Colosseum. So basically, here you can emulate a scenario. So basically, in Colosseum, everything is real-time, end-to-end scenario, except the over-the-air transmission. So for example, you can create a scenario here. For example, this is a parking lot scenario in our office, where we can create several G0Bs and UEs, and you can instantiate these things in Colosseum. So here we are using also OpenAI interface, GNodeB and UE. So for now, we just created this simple preliminary scenario of using line of sight path and with no fading. So at least the end-to-end system is working. So what our end goal is to actually come up with a real-time 5G NR positioning experimentation platform in Colosseum. So this is actually really missing in both academia and industry. So the idea is that either you can use, for example, site-specific thing. So for example, you can use a ray tracing tool in the site-specific, and you can come up with certain channel model. Or you can actually refine them with over-the-air experiments. So here we are using the OAI GNodeB and UE doing the channel measurements. So you can think of fusing this ray tracing and the real-time measurements, coming up with a channel model, and inject this channel model into Colosseum. And with using the open-air interface GNodeB and soft UE, you can do all the experiments. So the downlink TDOA or the RTT measurements. So this is will be a very valuable tool for the researchers working in localization and positioning. So they can actually test their algorithms on a realistic scenario with end-to-end 5G stack. So to conclude, so there are several experimental platforms at our institute that can be used to actually implement the research in a real-time system and to see, like, if it's actually working, or even better, that some of the methods that you proposed can be like standardized as well, right? Since there is a proof of concept. Yeah, thank you for inviting me.
Thank you. Any question from the audience? Yes, Rajeev.
Thank you for a really nice talk. For your CBRS capability, so you can quickly detect that there is the primary user, the incumbent is alive. Can you also quickly detect they are off? So both happen very quickly, or do you have some hysteresis?
So basically, we are doing like sensing periodically, so we can sense if they're on or off. So if you see that if it's just a background noise or interference, then you don't do any PRB blanking. But if you see, as the moment you see a primary user, you do the adjustments in your scheduler.
So if they're on for 2 seconds?
Yeah. Okay. Yeah.
So you can accommodate just 2 seconds, you don't use the channel.
Exactly, yeah.
Thank you.
Okay.
Yeah, I have this is my microphone. Okay, I can just speak here. No, the microphone's over there. So I think that it's good to see the Colosseum, the one. Some of you may not know, Colosseum was initial version 1 was built by Johns Hopkins APL, and a few years back, I think I went to Northeastern. Yeah. I'm so glad to see that's really taking advantage of and enhancing it in a great way. All right, thanks again, Rajeev, and we have a small gift.